So, we're going to discuss subparticles of an atom. So after which we're going to consider questions from the past questions. Yes, this is specifically for JAMB. So the idea is, do you know that the atom of every element is made up of the protons, the electrons, and the neutrons. So every element is, the atom of every element is made up of protons, electrons, and neutrons. No doubt, if you watch some of my videos, I had explained how to getting the number of protons present in the atom of an element. I've explained how to getting the number of electrons and the number of neutrons. So what I just have to do here, you'll see the reason we are having this class. Now the idea is, do you know that the proton of every element is centered in the nucleus? So this particular thing here is found in the nucleus of an atom, while the neutrons as well is found in the nucleus of an atom, but the electron is found in the orbitals or shell. Now this is what I'm trying to say. Now my emphasis is on electrons. Now pay attention. Now as regard to this particular thing here, there are certain rules. Don't forget I said this is found or located in the nucleus. This is as well located in the nucleus. Now this one is located in orbitals. Now there are certain rules. Now having explained or having said that, how do we get to know how electrons are arranged in orbitals? Now there are three principles to consider. I'm going to consider three basic principles. There are three principles to consider. You understand? Now the number one principle is called the half-bows. We call it the half-bows principle. The number one principle is called the half-bows principle. So let's discuss half-bows. We have half-bows principle. The number two principle is called the police exclusion principle. Police exclusion principle. The number third is the Ohm's rule of maximum multiplicity. Ohm's rule of maximum multiplicity. Now, these are the three rules to determine how you can arrange your electrons in an orbitals. Now, I'm going to start with the first one, which is the half-bows principle. You understand? It's either you call it half-bows or you call it the build-up rule. Now, as regard to half-bows, let's see what half-bows came up with. Now, half-bows principle states that electrons in an orbitals occupies the lower energy level first before moving down to the higher ones. Are we together? Electrons in orbitals occupies lower energy level first before moving down to the higher ones. Let me explain what that means. Now this is the idea. Don't forget, basically there are four basic orbitals. Now there are four basic orbitals, like I already told you. We have the S, the P, the D, and the F. Now the S orbital, I'm going to tell you what it's the name and the structure. Now for the S orbital is called the sharp, and it has a spherical shape. The P orbital is called the principal, and it has a dumbbell shape, or it has a bilobe shape. The D orbital is called the diffuse, and it has a double dumbbell shape or a cloverleaf shape. Then the P orbital called fundamental, and it has a complex shape. Now, as regard to Abel's principle, Abel says electrons occupies orbitals with lower energy level before moving down to the higher ones. Let me explain that. Now, this is the idea. Before I go into that, do you know that the s orbital can take a maximum of 2 electrons? The p orbital can take a maximum of 6 electrons. The d can take a maximum of 10 electrons. The f can take a maximum of 14 electrons. Take note. Now, as regard to what I have here, don't forget, according to orbital representation, the idea we come from 1s, from the s orbital. Now, I'm going to show you something. Down to 2s, 2p, 3s. Now, as regard to orbitals representation, we are from 1s orbital down to 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6d, 6f, and so on and so forth. Now, as regard to this, how then do I interpret Abel's principle with this idea? Simple. Listen. Now, the idea is electrons occupies orbital with lower levels before going to the higher ones. Listen. Now, do you know that 1s, the 1s, I'm going to show you, before I show you this one, let me quickly show you a quicker way of getting or knowing how to arrange electrons. Don't forget the rules now. We are seeing how to arrange electrons in orbitals, and these are the orbitals, s, p, d, and f. Now, the idea is I can represent this using an arrow. See what I have here. See the way my arrow comes. Take note of how the arrow comes. So that means orbital, I come from orbital 1s to 2s. Are we there? From 2s to 2p. 2p to 3s. 3s to 3p. 4s. 3d. 4p. 5s, 4d, 5. Now, let me take for example, let's say I want to write, and now the idea of Abel's can be used to write electronic configuration of elements. So that means if I want to write an electronic configuration for a specific element, all I needed is Abel's principle. Let's go. Now, take for example, let's take for example, let me say I want to write an electronic configuration for sodium. Sodium is the 11th member in the periodic table with an atomic number of 11, mass number 23. Listen. Now, how do I then write an electronic configuration for this element? The idea is, don't forget I've shown you how this is arranged based on Abel's. Now the idea is electronic configuration is a function of the number of electrons. Simple. First of all, you need to estimate how many electrons is present here. The idea is how many protons is there? 11 protons. Atomic number of protons. How many electrons is there? 11 electrons. The rule is for an electrically neutral atom, the number of protons equals the number of electrons. Simple. The idea is what do I mean by electrical neutrality? Or when you say an element is electrically neutral, listen. Now, take a good look at these two. Now, one of them is electrically neutral, while the other is not. Now, look at this. Now, I am trying to show the difference between this and this. Now, what difference is between these two things here? Listen to me. The idea is, you notice one of them had a charge. One of them is an ion. It has a charge, a positive charge. What are ions? Ions are a group of charges, whether positive or negative, cations or anions. Simple. Now the idea is any one of them, or rather all ions, this is pronounced sodium ions. So generally, all ions are not electrically neutral. So that means any atom with a charge is not electrically neutral, while all atom without a charge is electrically neutral. Simple. Am I making sense? Good. Now the idea is, from this sense now, I know there are 11 protons. I've explained that before. Atomic number of protons. Here, likewise, there are 11 protons. Simple. Now, how many electrons are here? How many electrons are here? Don't forget, for an electrically neutral atom, this atom is electrically neutral because it is not an ion. Therefore, the number of electrons is 11. Take a good look at this. Now, one thing you need to understand is that here, plus denotes or represents loss of. Now, I said minus denotes gains of electrons. Pay attention. Pay attention. Now, how do I get to know the number of electrons here? Simple. Look at this particular sign here. What sign is here? This is a cation, a positively charged ion. Simple. Now, because it is positively charged, that tells you that the atom of this element has lost one electron, making the number of electrons reduced by 1. Instead of 11, the number of electrons has gone down to 10 because 1 electron has been lost. Simple. Now, for the sake of the neutrons, simple. Don't forget, this is the mass number or the nucleon number. And nucleon number or mass number comprises of protons and neutrons. Since you already know the number of protons to be 11, equally, the number of neutrons would be 23 minus 11, which is a 12. That's not where I'm going to. Now, listen. Listen to me. As regard to this, how then can we write an electronic configuration for this particular element? The electronic configuration, don't forget, all I needed to know is how many electrons are present here. 11 electrons. Simple. Now the idea, don't forget, from about electron, lower energy to higher ones, I come from 1s, there's an arrow I showed you before. From 1s to 2s to 2p to 3s. Then, now, shall we go? From 1s, and I already told you that the s orbital can take a maximum of 2 electrons. So I have 1s2. After which, from 1s, I move down to 2s. 1s to 2s. Don't forget, the s orbital, the highest you can have is a 2. Then, from 1s to 2s, provided it is an s orbital, the maximum you can have is a 2. 2s2, 2 and a 2 is a 4. And I'm going to 11. How many more is needed? I need 7 more. So from 2s to 2p, the p orbital can take a maximum of 6 electrons. 2p6. Since I still have 7 more, after 2p is 3s. Now, how many more is needed? I am going to 11. 2 and 2 is 4. 4 and 6 is 10. 10 and how many more do I need to get 11? I needed 1 more. Let's go for magnesium. Magnesium is the number 12 in the table. So if I have to write something like this, simple. 1s2, 2s2, 1s2, 2s2, after which I move down to 2p6, 3s2. The idea is simple, learn to understand. So from what I had discussed here now, let's move down to the next principle, which is the Pauli's exclusion. Now, what does Pauli's exclusion say? Pauli's exclusion principle says or states that no two electrons. Now, for the Pauli's exclusion says no two electrons of an atom must have the same value for all 4 quantum numbers. Let me explain. Now, Pauli's is a very simple principle. Pauli's is trying to tell us that no two electrons. First of all, before I go into this, let me take us back to the concept of the orbitals again. Now, for this particular orbitals, don't forget I told you the s orbital can take a maximum of 2 electrons, 6 electrons, 10, and 14. Now, do you know that the s orbital has just 1 degenerate? The p orbital has 3 degenerates. 1, 2, 3. The d has 5 degenerates. Simple. Just take the number of electrons, divide by 2, and you get the number of degenerate orbitals. Now, from that sense, the next thing to find is how do I interpret Pauli's principle? No two electrons in an orbital must have the same value for all 4 quantum numbers. These are the 4 quantum numbers we discussed. Now, from this idea, now Pauli's is trying to tell us that no two electrons must have the same value for every positive or up spin. It is represented with a plus half, and for every opposite spin, it is represented with a minus half. So it is impossible, listen, it is impossible for you to have 2 same or similar spin, because the rule says they must not have the same value. So in a case where I have something like this, so no 2 electrons of an atom in an orbital must have the same value for all 4 quantum numbers. See, now for every degenerate orbitals, then they must have opposite value. It must be oppositely spin. That's what Pauli's is saying. That if you have one spin in this manner, then the other spin must be of an opposite value. They must not have the same value. That's the rule. They must not have the same value. So it is impossible of you to have something like this and still have something like this, because automatically you are disobeying this principle. They are having the same value, which is not supposed to be. So definitely you are supposed to have something like this. So they have opposite value. Simple. Now that is that. Let's consider Ohm's rule of maximum multiplicity. Let's consider Ohm's rule of maximum multiplicity. Of maximum multiplicity. Now what does this rule say? Ohm's rule of maximum multiplicity states that in a degenerate orbital, I have explained degenerate orbital before. In a degenerate orbital, electrons occupies each orbital singly. I'll go back again. Electrons occupies each orbital singly before pairing takes place. This is what they are trying to say. I'm going to use sodium again as an example. Let's go. Now, in this particular, I have explained this to you, so this is not new to you, yes. So how do I represent sodium in a Now, I want to represent this particular electron, electrons of this particular element in a degenerate orbital. And I need to follow Ohm's rule. Are we together? Listen. Now, don't forget the s orbital. As I rightly told you before, I said the s orbital has one degenerate. The p orbital has three degenerate. And the s as well has one degenerate, three degenerate, one degenerate. Now let's view. Now this is 1s2. You would notice how many electrons are there in the s orbital? 2. So you go with the first spin and you go with an opposite spin. So I'm done with this. Move down to the next one. I go with this and I go with this. Are we together? Just consider the number of electrons here. Then this one, I have 2p6. I go with the first, don't forget the rules. Electrons occupies each orbital singly, one after the other first, before you start to pair. So, I am going to 6, but the rule is I must fill them one after the other first before I pair. 1, I'm going to 6, another one. How many more is needed? 3, then I start to pair them. And for this, I have something like this. Are you following? Now, questions can come from this area. Somebody can just ask you, how many unpaired electrons are there in this particular... At times, they won't give you something like this. You are the ones to develop something like this. Don't forget, don't worry, we're going to solve examples as many as we can. Now, the idea is, how many unpaired are here? This is a simple language. Now, how many unpaired electrons are here? Simple. The idea is, let me use husband and wife to explain this. Do you know that naturally, to every husband, there must be a wife? For real now. To every husband, to every wife, there must be a husband. Now, this is it. To every positive spin is a husband, and to every opposite spin is a wife. That means it is assumed that every husband is expected to have a wife. Expected, I didn't say mandatory. Expected to have a wife. Now, when I now say unpaired, that means any husband without a wife is unpaired, or any wife without a husband is unpaired. This one here is the husband. If it has no this, it is unpaired. Simple. Now look at this. How many unpaired are you seeing here? From the look of things, this is balanced. So this one, I'm seeing a full option. You understand? So if you consider the orbitals here, I notice I have a positive and a negative spin. So this one is completely filled. This is filled as well. This is filled. Only this part here is not filled. So I have just one unpaired electrons. One unpaired electrons. Are we there? One unpaired electron. So that's another question. That's one area JAMB likes coming in. So the idea is how many unpaired are there. All you just need to do, you must be familiar with how to representing the electrons in orbitals. Simple. After which you can develop or tell the number of unpaired. Now let me give you another question. Let's see. Okay, how many unpaired electrons are there in... Don't forget, what will be the electronic configuration? Before I go into that, shall we write an electronic configuration for fluorine? Don't forget fluorine, 1s2, 2s2, that's 2 and 2 is 4. How many more is needed? I needed just 5 more. So I have 2p5. So how then can we represent these electrons in a degenerate orbitals? Don't forget, the s orbital has one degenerate s, one degenerate p, 3 degenerate. Now for a degenerate orbital, you're familiar with the rules now. For a degenerate orbital, electron occupy each orbital singly before they start to pair. So for this one now, this is going to be a full pair, a complete spin, a positive and a negative, or a positive and negative because of this two. The same way this is going to be same, but this, now don't forget the rules. You have to fill them one after the other first before you pair. So I am going to 5, I have 1, 2, 3. How many more is needed? I needed 2 more. So I have 1, then another one. So how many unpaired do I have here? I have just 1 unpaired. Now there is a very sweet, a very fast trick to getting the number of unpaired electrons other than doing all of this. Simple. The idea is, if I consider, look at this. For this one, how do I get to know the number of unpaired? All you have to look for, be on the lookout for, is go through the electronic configuration. So there is a faster way to getting the number of unpaired other than writing all of this. But all that's needed is to understand. So shall we go? Now in this case, I said what you should be on the lookout for is, you must be on the lookout for the number or which orbital is not completely filled. By the time I look at this one, S orbital can take a maximum of 2. This is filled. Go to the next one. This one, S orbital 2 is completely filled. P6 is completely filled. Only this orbital is not completely filled. And that is why my emphasis will be on this particular one. And don't forget, for the S orbital, the maximum number of electrons is 2 now. Yes. Now because I have 1 here, all you have to do to get the number of unpaired, these 2 here, remove this one from the 2 and you get 1 unpaired. Go for this one. This is completely filled, this is completely filled, this is not completely filled. So to getting the number of unpaired is quite easy now. All you have to do, simple. Now, since this is the part that is not completely filled, only the p orbital is not completely filled. Then what I will do is, how many electrons, what's the maximum number of electrons the p orbital can fill? 6 now. So to get the number of unpaired, 6 minus 5, you get 1 unpaired. From the look of things, how many unpaired are you seeing here? Just 1 is unpaired. And that's how you answer questions. This is JAMB. There's a faster way to getting all this answer other than the normal way. Now, let's then answer this particular. What if I ask you to find the number of unpaired? The number of unpaired in 3D, let me say 6.